Good morning, professors and judges. I'm Chen Xiyue from Puqing Middle School. Today, I'm delighted to share my paper on 6 free extraordinary numbers. Let's begin with a simple question on number theory. Given a positive integer m, how can we find the smallest integer m having n positive divisors? The simplest way is to find the number of divisors of the integers one by one. However, this method only holds for small values of m. Let's try another way. When n is equal to 12, there are 4 possible factorizations of n, with 4 corresponding values of m. In this case, the smallest one is 60, which is obtained when n is in the prime factorization. The integer behaves like this. We call it ordinary numbers, as stated in definition 1.4. In other cases, when n is equal to 8, the smallest one is 24, which is not obtained when n is in the prime factorization. The integer behaves like this. We call it extraordinary numbers. With the definition, we have the question naturally. Can we classify all extraordinary numbers? I've conducted some literary review on this topic. In the paper of R. Brown, he showed 3 properties of extraordinary numbers. And the second one stated out all square-free integers are ordinary numbers. In the main reference of my paper, Y.G. Ching generalized the result of square-free integers into 5 free integers. Here, 5 free integers means all integers which is not divisible by any fifth power of any primes. The main result of Y.G. Ching's paper is the list of all 5 free extraordinary integers, as stated in Theorem 2.1. It inspired me the most. I wonder if I can take it further. Finally, I succeeded obtaining Theorem 2.15, which is the main result of my paper, the list of all 6 free extraordinary integers. It contains all integers in F5, some additional integers, and some infinite families of extraordinary numbers. In this presentation, I will go through the proof of my main theorem in my paper and also discuss some extension on such infinite families numbers. The logical flow of my paper is following the approach of Y.G. Ching papers. I divided it into 5 steps in my paper. However, since there are more cases handling in 6 free integers, I will introduce Corollary 3.5 to reduce the complexity of the cases handling. Firstly, for each factorization of n, we can represent it by a descending sequence t. Then we can define the function at be the least values of n having n positive divisor for such factorization. Using this notation, we have proposition 2.4, which gives an equivalent statement of ordinary numbers. It can be used to prove the theorem 3.1. In step 2 and 3, I will find some necessary conditions for 6 free extraordinary integers. Before this, let me define some notation first. For non-prime factorization t, we can obtain the sequence tk by replacing the composite term tk by its factors ak and bk. Here, ak is the least prime factor of term tk. Using this notation, we have proposition 2.10, which gives a necessary condition for the values of at and atk. For example, when n is an extraordinary number 8, we can have a sequence t being 4, 2, such that the value of at is less than the values of atk. Theorem 3.2 and 3.3 are consequences by the proposition 2.10, which gives limitation of the length of the sequence t and also the position k for the composite integers in the sequence t. In summary, we get 3 necessary conditions for 6 free extraordinary integers. Notice that these 3 conditions focus the attention of the finite set of the d and k. Then by using program B, I can get all possible values of k, which is 1, 2, or 3. In step 5, I will further divide the cases into subcases depending on the values of b, a, and tk, as this table shows. If such case is valid, I will prove that I will show that it will produce an integer n belonging to F6. Before this, let's see how can we identify the invalid cases. For the simple case like case 3a, after applying lemma 2.13, we can get the lower bound of D. Then by the assumption of 6 free integer, we can get the upper bound of D. Since it produces a contradiction of the bound of D, this case is invalid. This table shows all some invalid cases which can be eliminated due to the similar arguments. For the remaining cases, we should compare the values of AT and ATK to check whether it satisfies the necessary condition or not. Proposition 2.11 gives a formula to calculate the quotient in YG Chang paper. However, it is not applicable for 6 free integers since it can only give a wide range of the quotient. It is not effectively to reject the invalid cases. Therefore, I have Ferrari 3.5, which is a new tool to handle to effectively reject the invalid cases. Although we cannot know the exact values in T, we can find a sequence S containing sequence T. Then, Ferrari 3.5 can then be used to find a tight lower bound of the quotient, depending on the free values RA, RB, and D. Then all possible values of T can be further divided into subcases depending on these free values, and I write program D to calculate all possible minimum values of the quotient for each subcases. For the similar cases like case 3I, after using Ferrari 3.5 and program D, I will get all minimum values of the quotient, which for the give all possible values of RA, RB, and D is less than 1. Which contradicting the necessary conditions. More cases can be eliminated due to the similar arguments. For the remaining cases, only a few T with the quotient is less than 1. Then we can get all possible value of RA, RB, and D, just like the table shows. For each subcases, the conditions of T is enough to determine whether the factorization T is valid, and we can check that it produces an N belongs to F6. From now, the proof of my main theorem is finished. Let's review the main result of my paper again. And we find something interesting. There are some infinite families of extraordinary numbers belongs to F5 and F6, but not in F4. Can we do some deeper research about it? I list out some examples of such infinite families of numbers. Notice that both of them are generated by 1 prime. Are there some infinite families of K-free extraordinary numbers generated by more than 1 prime numbers? So I propose the question below. Given a positive integer S, how can we find an integer K such that there exist an infinite families generated by S primes belonging to Fk? Furthermore, what is the minimum value of K? For example, when S is equal to 1, the minimum value of K is 5, since there is an infinite family in F5 but none in F4. Begin with the condition in the questions. I observe that there is a factorization T with the quotient is less than 1, just like the proposition 2.4 show. Then by proposition 4.2, which have with the proof in my paper, I get T1 to Ts are equal to Q1 to Qs, respectively. Then the first S terms of the numerator and denominator of the quotient is the same, which can be cancelled out each other. It inspired me to generalize the definition of the function AT and the ordinary numbers. Firstly, the definition of the function AT can generalize it into AUT by offsetting the first U primes in the function AT, just like the definition 4.4 show. Then, after replacing the function AT into AUT in proposition 2.4, we can generalize the definition of U ordinary numbers from ordinary numbers, which holds proposition 4.5. Then, the question about how to find an infinite families generated by S primes is equivalent to ask how can we find an S extraordinary numbers. So the question can reformulate it to a new question using the new definition. Given the positive integer S, how can we find K-free S extraordinary numbers? Since most of the definition and proposition in my paper can be generalized by the similar setting, it is reasonable to say that we can solve this question due to the same idea of my paper. This is the end of my presentation. Thank you for listening.